All right, so now what we're going to do is we're going to continue on with our look at cognitive psychology. And today we're going to tackle a special topic. We're going to take another look at representation. And then we're going to apply it to the idea of artificial intelligence. And at the same time, kind of really get into how cognitive psychology views our minds at the same time. So this is going to be that special topic, representation and AI. We are going to have a very quick recap on information processing systems. We're going to have a quick recap on Marr's tri-level hypothesis and just on the idea of representations and the Pandemonium model solution. So the sort of take-home exercise that I gave, we'll take that up in class right now. Hopefully you were able to solve those. And then we're going to take a look at artificial intelligence. Why is it important? Why is artificial intelligence often lumped in to cognitive science with cognitive psychology? And it's all tied to the physical symbol system hypothesis, and it's tied to the idea of a Turing machine, and we're going to take a look at Turing machines and the very famous Turing Test. All right, so a quick recap about the information processing system. So again, the entire idea behind cognitive psychology is that we're information processing systems. That's what our mind is. So we take information from the external world, and that goes into our mind, and then we take additional information, and that goes into our mind, and we take additional information, and that goes into our mind, and then we somehow represent that information with internal symbols. We manipulate those internal symbols to come to new representations, and then we can further manipulate those new representations with internal representations such as memory to come up with new representations which can then lead to action. So in this case, we decide that we're looking at a stop sign, and then we would decide if we were driving a car, then now would be a great time to stop. Recall Marr's tri-level hypothesis, and this is very important to know for the purposes of this class, because if we want to fully understand an information processing system, that is, if we want to fully understand our mind, we need to answer the following three levels. We need to address the following three levels. Level number one, computational level, we need to know the problem that we're trying to explain. That is, we need to know what it is that a human mind can do. So we can remember up to 7 plus or minus 2 digits in our working memory. We can alphabetize lists. We can navigate the world, an environment. We can perform on Jeopardy. We can get distracted when noises occur outside. All of these things are the things that we can do. So we first need a list of everything that we can do. Once we have that, we've solved the computational level. Next thing we have is the representational level. Representational level are the strategies that we use to solve the computational level. So how could the computational level be solved? What are the possible strategies for alphabetizing a list of words? What are the possible strategies for navigating a room so that you don't bump into furniture? What are the possible solutions for the things that we can do in the computational level? And then the implementation level is how is that actually done in a real thing, in a real solid physical entity. So this implementation level is the domain of neuroscience. So we are not going to get there because that's another course entirely. This is the domain of cognitive psychology. This is where we're going to sit. So we're not going to talk about the brain. We're not going to talk about axons and neurons and different types of connections. That's neuroscience. But what we are going to talk about is in our mind, in this sort of concept of where we represent all this information, what are the possible solutions that our mind is doing in order to be able to do the things that we have at the computational level. All right, and remember that we had the idea of a representation. This is an internal cognitive symbol that stands for some external reality. And one of the big challenges in cognitive psychology is that these different external realities can be represented in multiple ways in our internal information processing system. So the idea of two-ness the idea that there's two of something can be represented with a variety of internal symbols, and a cognitive psychologist's job is to figure out what symbol is actually being used. Because while we can use a variety, our minds are typically only using one form of representation, so we need to try to figure out what is that representation. And again, this is crucial because in some cases, a representation will make things possible, and in other cases, it'll be impossible. In some cases, a representation will make behavior very easy. In other cases, it will make it impossible. So this representation of this external reality will make it very easy to estimate the distances between two cities, Los Angeles to New York, 2,790 miles. It would make it impossible to estimate which city is further north. This representation makes it possible to indicate which city is further north. It's New York right there. It makes it difficult to indicate what's the distance between the two cities. So again, the internal representations have implications on behavior. That's why we can measure behavior and figure out what those internal representations actually are. All right, so that's your quick recap on last class. So what we're going to do right now is we're going to take a look at the Pandemonium model solutions. So just by way of review, recall that this model is a representational level explanation for how is it that we recognize letters. So nobody is trying to say that somewhere in our brain we have these little demons running around. But what they're saying is that this is a possible strategy for how our mind can solve letter recognition. So if we have a P here, it's going to get projected onto the image demon. Image demon sends this up to the TV here that the feature demons can watch. If the feature demons see the feature on their belly on this screen, they get very agitated, very angry, and they need to tell somebody. So they send a message to all their connections, and their connections end up in this cognitive demon room. The cognitive demon room has demons with letters on their belly, and then these demons simply indicate how many people in the feature demon room are complaining to them, and that gets sent to the decision demon, and whoever has the most complaints ends up being the letter that is recognized. So that's a quick overview of the letter recognition system. So let's take a look at what would happen with this model right here if we saw the letter P. So we got the letter P, and that gets, we'll take it through the system, we'll walk it through. So hopefully you did this on your own so you can kind of check your answers against what's going to happen right now. So this P goes into the image demon. Image demon sends the image up to the screen there. And then the feature demons, looking at the screen, start getting agitated if a feature matches what's on the screen there. So that first demon, vertical line on its belly, sees a vertical line on the screen, gets agitated, and sends a message to that demon, and to that demon. And lets them know that it's really hot and bothered, it's seeing this feature and it can't believe it. The feature on my belly is on the TV, and it gets really, really angry. This second demon over here also sees its feature on the TV, gets really hot and bothered, and then sends messages to its cognitive demons that it's connected to. And then interestingly, we have this demon over here, which sees nothing, it doesn't see its feature. We have this demon over here, which doesn't see its feature either. So we then go to the cognitive demons, and we got cognitive demon R there saying, well, I've been told by two people, two feature demons have contacted me saying that they're all hot and bothered. And this cognitive demon here says, I have also had two people contact me saying they're all hot and bothered. Cognitive demon F says, I've had one person contact me. Cognitive demon Z doesn't even know that an image has been shown because nobody's contacted it. So we got 2, 2, and 1. And what that means is that this decision demon is going to be confused. Because this decision demon does not know which one of these to pick. Because it picks the cognitive demon that has the most complaints being sent to it. And in this case, there's a tie between an R and an F. So this decision demon would be unable to recognize this letter. And this letter looking at it, they wouldn't know if it's a P or an R. In this system, it would be very, very confused, and that's prediction from this Pandemonium model. Any questions about that analysis? All right, let's take a look at the second challenge, second take-home challenge. So we'll reset the system, and this time we're going to ask the question of what would happen if you had an injury that severed one of the connections between the feature demons and the cognitive demons. So let's say that you had a traumatic brain injury and you lost that connection as a result of that injury. What are the behavioral consequences of that injury according to this system? Well, this time we're taking a look at an R, and if you remember previously, no problems whatsoever recognizing an R. Cognitive demon R had 3 people complaining to it. That was the highest number. Decision demon easily said, yes, we're looking at an R. What about right now? Well, we go through the steps again. Image demon gets the image onto its belly, sends that up to the TV screen there, gets projected to the feature demons. Once again, they see features of themselves on that screen and start getting agitated. So that demon sees the vertical line, gets agitated, sends complaints to its connections. And then we have this demon here, it gets agitated and it sends complaints to its connections. And then we have this demon over here, it doesn't see the feature on its belly, so it's not bothered or hot or bothered or anything. And then finally we get to this demon over here, and it does see its feature, so it does get activated, it does get hot and bothered, but it can't send its message to anybody because it lost its only connection. So while this demon is angry, it has nobody to contact, nobody to send that message to because it's lost that connection. Continuing on with our analysis, we see that this cognitive demon now has been contacted by 2 individuals. We see that this cognitive demon P demon has been contacted by 2. The F demon has been contacted by 1. The Z demon has not been contacted at all. So we have 2 demons saying that 2 people have contacted them, and the decision demon in this case would be confused. So an analysis of this model here would indicate that after a brain injury, if this connection was lost, number one, we would be confused when we're looking at R's and P's. So we would be confused and we wouldn't know, am I looking at an R or am I looking at a P? So that would be one prediction, that we would be unable to tell the difference between R's and P's. But notice also that there's another prediction. We would not be confused if we were looking at if we would not be confused as to whether we were looking at an F. So it's not as if this stimulus here would look like any letter and we just couldn't tell what letter it is. This symbol here, this external reality here, looks like either an R or a P to us, and we couldn't answer which one it was. But if somebody asked us, is it an F? We would tell them, oh no, it's definitely not an F. There's no confusion as to whether I'm looking at an F. What the confusion is it a P or is it an R? So it'll let you, a model like this will let you predict what letters should be confused and which ones should not be confused with each other. All right, so that's our wrap up of the Pandemonium model. Any questions about what we covered last class, the representations, Pandemonium model, any of that? All right, on to the new stuff. Okay, so we're going to start off taking a look at artificial intelligence. And specifically, we're going to start with looking at why is it important. So the reason that it's important, well, why is it important for a psychologist? We'll take a look at that specifically. So if you're trying to understand human cognition, if you're trying to understand the human mind, why is knowing about artificial intelligence important? Because artificial intelligence is literally not the human mind, right? So why would we even think about going outside of psychology to help understand what the human mind is like? And it has to do with the idea of a physical symbol system. So a physical symbol system is kind of all there in the title. It has certain characteristics. Number one is that it's physical. It's something that is a physically realizable system. That means you can actually make it in the real world. You can actually put this thing together in the real world. So an abacus here is a physical symbol system, because you can make an abacus out of wood and metal and glue. So the first thing is that it's got to be able to exist in the physical real world. It has to have a bunch of physical patterns that can be strung together. So it exists in the real world, and it contains a set of symbols. It contains a set of representations, physical patterns, physical things that can actually be strung together. And if you learn how to use an abacus, you will learn how to string these symbols together. And once you have that physical realizable system, and you have a set of symbols in that system that can be strung together, you can then add a set of processes that operate on these symbols. So has anybody here ever used an abacus? Yeah, no, yeah. That's when they were the cutting edge. That was the original iPad. So if you're wondering how an abacus, the basics of how an abacus works, this row down here, these represent ones. So if you're trying to count, if you have one of something, you would take this bead and you would move it over to the right. If you have two of something, you would move 2 beads over to the right. 3 of something, you would move 3 beads over to the right. Once you get 10 of something, all of these beads go over to the right. At that point, you can move them all back to the left, and you can move this bead over to the right because this is tens. So this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And once you have all of those, you can move them back because this are the hundreds. So these are the hundreds, these are the thousands, these are the 10,000s, these are the 100,000s, so on and so forth. So you can represent large numbers using an abacus. And if you get good using an abacus, you can do the following. Okay, so we haven't used abacuses for like 100 years in our society, but they are used elsewhere. So this is a pharmacist in China, and they are, or a pharmacy clerk, and they are using an abacus, and you can see what kind of processes they're using. So she's literally doing calculations with an abacus. And you can just see she's following rules. She's manipulating those internal symbols according to rules to tally up and calculate, various numbers for that pharmacy. So you can get very, very fast with an abacus. And again, it has a set of rules that you can use to manipulate those internal symbols. All right, and then there's one last thing that a physical symbol system needs, and that is that it needs to be situated in a wider world, and it has to be related to that external world by designation and interpretation. So it needs these two things to be connected to that outside world. So what is designation? Designation means that you can take an external reality and you can represent it on your physical symbol system. So that pharmacist could take the external reality of, we need 100 pills, and she could represent it on this physical symbol system by taking this bead and moving it over to the right. She could say, all right, 100 in the external world means this bead is over here. That's how I designate that external reality. So designation is the way that the external world gets into the physical symbol system. And then interpretation is the way that the representations get back out into the external world. So what interpretation means is that somebody could look at this physical symbol system and interpret what the representations are standing for, what the representations mean. So for example, I can take a look at this abacus over here, and I can interpret this as signifying 0. So with my limited abacus skills, I know that when I'm looking at this, this is symbolizing the external reality of 0. And for that pharmacy clerk, when the pharmacist comes over and checks the abacus, the pharmacist can make sense of the abacus and say, oh, 1,482. That's what your abacus is saying. So interpretation is the ability to take a look at what is represented in your physical symbol system and make sense out of it. And if you have all 4 of those, you have a physical symbol system. You got something that can exist in the real world. It has internal symbols. These symbols can be manipulated according to processes, and they're connected to the real world by being able to represent external realities, that's designation, and then be able to go back into external by interpretation, by knowing what those symbols mean. All right, so any questions so far in the physical symbol system? Okay, so that's one example of a physical symbol system. What's another example? Well, the computers that you use, the cell phones that you use, they are physical symbol systems because they check off all of these criteria. They are a physically realizable system. They do exist. They're really here. They contain a set of symbols, physical patterns that can be strung together. So computers have a set of symbols of zeros and ones. They have a set of symbols of on and off. That is where we're currently at. They're going into quantum computing, which is a whole new set of symbols. But importantly, there's a set of symbols that can be strung together to make larger and larger patterns. These symbols contain, or this system contains processes that operate on those symbols. So we have programs that our computers run that tell us how to manipulate those symbols. It lets us know, when I get this symbol, this is what I'm supposed to do. When I get this symbol, this is what I'm supposed to do. And that's how we are able to interact with our phones and allow them to do, our computers. And that's how they can do that meaningful work. And then lastly, they are located in the wider world by designation and interpretation. So when you're using your computer, and if you're taking notes right now with your laptop, you can designate what I'm saying into your computer. You could put it into a Word document and say, these are the 4 characteristics of the physical symbol system. And then if you were to show that to somebody else, they could interpret it. And they could say, oh, those are the 4 characteristics of the physical symbol system. So a computer is another example of a physical symbol system. All right, I'll give you one more. And this is probably the most important for us. So, we'll get to the physical symbol system hypothesis. Jump the gun a little bit there. So why are we talking about physical symbol systems? It has to do with the following hypothesis that was put forward by Newell and Simon, 2 giants in the field of computer science. So there they are right there. And what they proposed, what they hypothesized, is that a physical symbol system has the necessary and sufficient means for general intelligent action. So a physical symbol system, something that can be made in the real world, something that has symbols that it can act on, something that has processes to manipulate that symbols, and something that's linked to the world with designation and interpretation, they hypothesize that that thing, that physical system, has the necessary, so it has what is needed in order to do general intelligent actions. And more importantly, it has sufficient. It has all that it needs to do general intelligent action. So if you have something that can do general intelligent action, and you're wondering, how can I understand this thing that can do general intelligent action? Newell and Simon's hypothesis say, you're probably looking at a physical symbol system. So, because any physical symbol system can do general intelligent action. So this was very, very important because it gave us our in to understanding human cognition. Because this idea of a physical symbol system that they proposed has everything that you need, and it has enough of what you need in order to do general intelligent action. This is very important because the last example of a physical symbol system is us. We are physical symbol systems. And if you take a look at the characteristics, we satisfy all 4. We are a physically realizable system, right? We exist, we're here. We are for real. we have a set of symbols in our brain, physical patterns, real, actual physical things that have that can be strung together. And these are your neurons with their connections and their synapses and their dendrites and all of that, you know, and their axons. So these are physical things that can be strung together. We have a set of processes that operate on these symbols. So you have connections that are excitatory, you have connections that are inhibitory, you have certain neurons connect to other neurons, they don't connect to other neurons. We have rules for how your brain operates, right? We have rules for how they're all connected together. And then importantly, we are located in a wider world related by designation and interpretation. So this is something that comes up over and over again in conversation. So if you're at your graduation and the chancellor says, congratulations on, or vice chancellor, or maybe former vice chancellor, I can't keep up sometimes. But if somebody says, congratulations on earning your degree, you are able to represent in your mind with your physical symbols this external reality, this congratulations. And you are able to manipulate those internal symbols so that you can come up with a response of thank you very much that is able to be interpreted by this external reality. So it is the complete system that we have. We can be thought of as a physical symbol system. So this physical symbol system hypothesis basically opens the door. It basically says we can do general action, right? We can do general intelligent action. We can do general cognitive abilities. Our computational level is just filled with stuff that we can do. So we're a general intelligence system. So how do we understand this? How do we understand what we can do? Well, we can start by saying we're a physical symbol system, because that has everything that you need and enough of what you need for general intelligent action. So the fact that we can do general intelligent action and the fact that we're a physical symbol system means that this is probably a great place to start. All right, any questions on that hypothesis and the idea of a physical symbol system? All right. So the question now is this actually true? So notice, and I kind of glossed over this, this was a hypothesis. This was them saying, we kind of figure that this is enough, but is it actually enough? And that is where Turing machines actually come in. So Turing machines are named after Alan Turing, and he is one of these just like mega geniuses that existed in our world. And he came up with the idea of a Turing machine. And his story has been told in movie form. It was Benedict Cumberbatch in The Imitation Game, if you kind of want a dramatization of what he went through. He was huge in code breaking during the war. But for psychologists, it was the Turing machine that is one of his most important contributions. And the Turing machine is a mechanism, it's a machine that has a finite number of programmed states, right? So it has a finite number of ways that the machine can be, states that the machine can be in, and it takes inputs in and gives outputs as symbols, so it can take in information and can give information out, and it has a finite alphabet. So it has a finite set of symbols that it can use. So importantly, nothing about the machine cannot be actually realized in the real world. Nothing about this Turing machine is fantasy. It's not like, oh, it needs an infinite number of symbols. Doesn't. Finite number of symbols, finite number of states. You can make Turing machines. In fact, you're all sitting in front of a Turing, well, if you're sitting in front of a laptop, you're sitting in front of a Turing machine. But you can make a Turing machine. So this is a simplified version of a Turing machine, just to kind of show you how it works. So what it does is that in some way it scans. It takes symbols as inputs one at a time. So here we have this tape. This kind of shows you how when this idea came out. So here we have this tape, and on this tape you can see these symbols, right? So we got X's, we got vertical lines, we got spaces. We got 3 symbols in this alphabet. And then we have this tape here, and this tape gets moved along and it gets scanned. And this scanner here reads what's on the tape, and then this memory dial tells you what state the machine is in. So the state of the machine can be in 6 different states, right? So a light switch can be in 2 states. It's either on or it's off. This machine can be in 6 different states, all right? And then it's got a logical control, and it's got a tape mover. It's got an eraser and a writer that can erase a symbol and then put in a new symbol, and then it's got the tape mover that brings out the output. All right, so that's the basic formulation. So it can scan. It can take symbols as inputs one at a time. It can erase the symbol, right? So one thing that it can do is it can erase the symbol or not. It can choose to leave the symbol alone, depending upon what the symbol is and depending upon what state the machine is in. It can print a new symbol or not. Once again, depending upon what the symbol was and depending upon what state the machine is in. And it can change state or not. So, for example, if it's in state 1 and it reads a vertical line, it might then decide to change to state 3. That might be the programming that is in this machine, right? So if you're in state 1 and you read a vertical line, erase that line, put in an X, and change to state 3. Those are the kind of instructions and processes that this machine follows. And then once it's done that, it moves on to the next symbol. So far, so good? All right, so why is this so important? Well, why this is important is, first off, it's a physical symbol system. So it is a physically realizable system. It contains a set of symbols. You can see them right there on the machine, physical patterns that can be strung together. It contains a set of processes that operate on those symbols, scanning, writing and erasing, changing the state of the machine. And it is located in a wider world of real objects related by designation and interpretation. So if you are educated in how to read these symbols, it's kind of like almost reading Morse code or reading Braille. You can designate things with these symbols, and then you can interpret the symbols that come out. So you can designate what to put into the machine, and then the Turing machine runs, and you can interpret what comes out of the machine. So it is a physical symbol system. So why is this particular physical symbol system so important? Well, what happened was Alan Turing proved, so this is not a hypothesis, this is a proof. He proved this, he showed this logically, without a doubt, that this can be done. So he proved that if you had enough time and you had enough tape, right? So you had enough time to run this machine and you had enough tape to designate what you needed to designate. He proved that a Turing machine can perform any computational task. Any computational task. So that machine that I just showed you, a Turing machine with a finite number of states, with a finite number of symbols, given enough time, can alphabetize a list of words. That Turing machine, with its finite number of states and its finite number of symbols, can navigate a room and not bump into things. That Turing machine can write a screenplay, given enough time and given enough tape. Right? That Turing machine can do any computational task given enough time and given enough tape, and basically you might be able to make some argument with this, but you can basically replace computational with cognitive tasks. And this really opened the door for understanding human behavior. Because if we can do just about any cognitive task, how do we begin to understand how we do it? Well, we're basically a Turing machine. And if we can understand a simpler Turing machine, then we can understand the more complicated Turing machines. So this really gave an in terms of what is it that our cognition is doing, what is it that our minds are doing. And it was massively promising because he proved this formulation, a machine with these characteristics, it can do any computational task. You just need enough time and you need enough tape. So that was a huge proof that basically opened up the doors for cognitive psychology. All right, any questions on the Turing machine? All right. So, in other words, Turing machines, they manipulate symbols, they define cognition in terms of manipulating symbols, and that's why in cognitive psychology, everything that we're going to see is all about manipulating symbols. Everything that we're going to see is all about how do we represent it, what are the symbols, and then how do we manipulate those. Because again, Alan Turing showed that this can be used to perform any cognitive task. All right, so if any cognitive task can be implemented by a Turing machine, the last question we're going to address today is how much cognition do you need for mentality? So this idea of having a mind, right? This idea of being able to think, this idea of having what we'll call it mentality, the ability to think, the ability the characteristic of having a mind. How much cognitive tasks are required before you would take a look at a machine and say, that thing has a mind? So that was a question that came up in Turing's time when they were really starting to think about artificial intelligence and basically saying, well, how much is it that we need in order to say this thing has a mind? We've created artificial intelligence. And for this, he came up with the Turing test. So let me just put this into context before we take a look at the Turing test. So let's say that you get hired by Elon Musk, right? Let's say that Elon Musk starts up a new company and says, or he might have already, I don't know. But let's say that he starts up a new company and says, we're going to be creating artificial intelligence. That's the one thing we're going to be doing here. We're creating an artificial intelligence. And you get hired as a computer programmer, and that's just your task. He's like, you're the person on this project. Go, write me a program, create some artificial intelligence. So you go away, and you're writing your program, and you write a program that can alphabetize lists. And you're like, all right, I'm going to show this. So you go back to Elon Musk and you say, hey, check and look, I did it. Look, I have a program, it can alphabetize lists. He's probably going to look at you and say, not enough, right? Keep going. I can't call that a mind yet. I can't call that mentality yet, so keep going. So you go back and you're like, all right, alphabetize lists and can count to 1,000. Great, got it. You take it back to him, he would still say, not yet. So you go back and you put in more stuff, and you come back and he's like, not yet. And you go back and you put in more stuff, and you come back and he's like, not yet. And you keep doing this, keep doing this, keep doing this. The question that we're asking here is, when are you going to put in enough stuff so that when you go to Elon Musk, he says, that's it, that's enough. This thing now has a mind. This program now has a mind. That's what this question is all about. When is it sufficient to say that this entity, this thing, this physical symbol system has mentality, has a mind, is able to think? So Turing, genius that he was, proposed the Turing test as a sort of test of mentality. And the Turing test goes a little something like this. So the Turing test is based on the idea that we know that we have minds. Right? So if you were to ask yourself, do I have a mind? You kind of go back to Descartes with that I think, therefore I am observation. But you can check in on your own mind. And you can kind of say, you know what? I do have a mind. I feel that I'm thinking. I have the introspection that I'm thinking. Something's got to be thinking, so I have a mind. So we know that we have minds. And we can get that by introspection, right? So we know that if you ask yourself, do I have a mind? Yeah, you can say basically, I guess that I do. But, and this is the huge case, we're sure that we have minds, but we believe that other people have minds. We believe that we're interacting with other people who have minds, and there is no real basis for this assumption. So if we, again, through introspection, we know that we have minds, but when I'm interacting with somebody, maybe they have a mind, maybe they don't. Maybe they're a real human being. Maybe if they fell over, their faceplate would fall off. I would see nothing but blinking lights and rods and gears and everything in behind the face. And I would be like, oh my gosh, they were a robot this whole time? I had no idea. So it's quite possible that they don't have minds, right? And this is a huge philosophical issue. But we assume that other people have minds. So when I interact with everybody in this class, I'm giving you the benefit of the doubt. I'm assuming that you have a mind, because I can't look into your mind. I can't introspect into your mind and say, oh yeah, there it is. They have a mind. So I know I have one, and I'm assuming that you do as well. So there's no real basis for this assumption. So Turing started asking, well, what is sort of the criteria that we look for? What is sort of enough for us to say, oh yeah, this person that I'm talking to definitely has a mind? And that was the basis for the Turing test. So I'll give you an example of what that is with the following example here. So let's say that you are an animal psychologist, and this farmer calls you over and says, you got to take a look at my cow. Something's weird. My cow seems, you just got to take a look at it. So you go down to the farm, and you start inspecting the cow, and you go, hello there, Mr. Cow. And the cow goes, moo. Would you all of a sudden say to yourself, oh my goodness, that cow has mentality. That cow has human level. Let's go with human level. That cow has human level intelligence. That cow has human level mentality. Would anybody say that? No. All right. So in this case, we would say no mentality, no human level mentality. Let's say that it went a little bit different. Let's say that you went up to the cow and you say, hello there, Mr. Cow. And the cow looked back to you and said, hi, Mr. Scientist. Right? At that point, you would be like, oh my gosh, whoa, what is this? This is the most amazing thing ever. And you would continue the conversation. You'd say, I didn't know cows could speak. And it goes, well, I'm a cow and I can speak. You're like, oh my goodness. And you'd be like, that's utterly fantastic. And the cow would say, that's lame. So in this case, if you were looking at this interaction, would you say that this cow has mentality, that this cow has a mind? Yes. So that would be yes to mentality. You would say in this instance, this cow seems to have a mind. All right, one more example. You go up to the cow and you say, hello, Mr. Cow. And the cow goes, hi, Mr. Scientist. And you're like, oh my gosh, a talking cow. I can't believe it. I didn't know cows could speak. And the cow goes, hi, Mr. Scientist. And you're like, could you say anything else? Hi, Mr. Scientist. In that case, would you say mentality? No. So this would be a case for no mentality. We have a very weird, unique cow. We have a cow that can say, hi, Mr. Scientist. But in no way does our interaction with that cow indicate the possibility that this cow has a mind, that this cow has mentality, that this cow has intelligence. So something about conversation, something about being able to carry on a conversation seems to be one of the criteria for, or sufficient criteria for mentality. It seems to be enough. If you can carry on a conversation at human levels, that seems to be one of the sort of hallmarks of, yes, you definitely have enough mentality. All right, and that's the basis of the Turing test. So the Turing test is framed as an imitation game. And what it is you basically have two rooms. In one room, you have the artificial intelligence. In another room, you have a living, breathing person. And then outside of those two rooms, connected through basically texting, you have a second individual. And what they do is they ask questions to each room. They ask a question to the artificial intelligence, they ask a question to the human, and they do not know which room has the human and which room has the artificial intelligence. So they start asking questions to try to figure out which one is a human, which one is a computer. So they'll ask things like, what is the capital of France? And the computer will consult its databases, get online, and it'll say capital of France. It'll send back the answer, Paris. And then the human would be like, yep, as well, Paris. So in this case, no information. right? No way to tell which one's computer, which one is human. You might send in another question. Which of the following would you most prefer? A puppy, a flower from your sweetie, or a large properly formatted data file? And the computer might say, I prefer C, and the human might say, I would prefer B. And in this case, now you're getting a little bit of information. So you continue on with this game, and if you can pick who the human is, then the computer has failed the Turing test, and we would say that the computer does not have mentality. If you cannot pick who the human is, then we would say that the computer passed the Turing test and that the computer does have mentality. So if the questioner identifies a room with a human at chance levels, that is, if it's 50-50, whether it says that the human is in the correct room or the incorrect room, then we conclude, according to the Turing test, that the computer actually does have a mind. And this is basically giving the computer the same benefit of the doubt that we give other people. Because when you interact with other people, we assume that they have minds based on their behavior. So when we interact with a computer, we want to give it the same benefit of the doubt. We're going to assume that it has a mind based on its behavior. And conversation and the ability to speak seems to be one of the hallmarks of what is sufficient, what is enough to say that somebody actually has a mind. So passing the Turing test is a sufficient condition, and I mention this because it is important to remember this is sufficient. So what I mean by that is that if we have, I'll just draw this line here, if we have conversation here, and this is the line. Below here is below human conversation. Above this is a passing human conversation. And you have something that makes it here. According to the Turing test, this thing definitely has a mind, right? It's sufficient. Once you pass that conversation stage, that's sufficient to say that you actually have a mind. But if you don't pass it, that does not mean that you do not have a mind. Right, so it's important to remember that. Passing it means for sure you have a mind. Not passing it does not mean that you do not have a mind. It just means that we cannot be for sure that you have a mind. So think about things like babies. Right? Babies would fail the Turing test. Right? Try a Turing test with a baby. You're not going to get any responses, right? Not until much, much later in life. Things like animals, right? Animals have minds. Animals would fail the Turing test. So this is not to say that babies don't have minds and animals don't have minds. They might have minds, but the Turing test says that if you pass that conversation threshold, then you definitely have a mind, because that's the thing that we use to assume that other people we interact with have minds. So it's giving computers that same benefit of the doubt. It's using the same criteria for computers. So another thing that would fail the Turing test, I'm painting myself into a corner here, is mannequins. Don't know how to spell mannequins, so we'll just lean into it. Mannequins would not pass the Turing test, right? They look like humans. They're they cross over into that uncanny valley, which is why some people don't like mannequins. But they would definitely fail the Turing test. Mannequins look more like humans than babies do, right? They look more like us than babies do. So it's not a physical thing. You cross this, you definitely have a mind. You don't cross it, maybe you do, maybe you don't. So that's what we mean by sufficient. All right, any questions on the Turing test or the ideas behind the Turing test? All right, so we're going to wrap up this class today. We just mentioned that it's a sufficient condition, but is it necessary? And the answer for that is maybe. It might be necessary, but then it might not be necessary as well. So you might need to pass the Turing test to show mentality, but it's not necessarily the case, and I'll show you why in just a moment. But if this has piqued your interest, and you want to try to solve the Turing test, There actually is a Loebner Prize in Artificial Intelligence that is awarded to whoever comes the closest to actually passing the Turing test. So we actually have products right now that come close to passing the Turing test. So things like Siri and Alexa come close to engaging in conversation, but we still know that they are artificial intelligences. So this is actually a prize, and people have come close. There's an annual Turing test contest. The prize is actually $100,000 and a spiffy gold medal. It has never been won. People have never made a program that can successfully pass the Turing test. So I put 2 links there, and you can try these out on your own computers. But there are 2 links here to computer programs that have made it close. So these are some of the ones that have gone the farthest. So, you know, this is called Jabberwacky, and it is basically a Turing test. So do you hold out hope for a better time? Anybody want to engage in conversation? All right, so I didn't hear any screams, so I'm eternally optimistic. You are slow and old. Oh man. Oh yeah, okay. I'm in the prime of my life. Who is your father? Okay, so you can see we can't be related. All right, so you can kind of see it's gone off the rails. Something's fishy here. If you were interacting with a person and they were responding to you like this, you would basically start questioning if they're all there, right? You'd be like, are you, something's not right. Clearly something is wrong here. It's difficult to pass the Turing test. So that's Jabberwacky. The other one is Mitsuku over here. And I'm going to refresh this. You should have a little chat thing that'll pop up here. But if it doesn't, this is another interactive one that you can test out. You can try it out on your own, see how convincing these programs are, see how far they've come. And again, see sort of, how does it feel when you're interacting with these individuals, and see if you can, if they would actually pass the Turing test. So that's one way to try to pass the Turing test, but as it kind of stands right now, we're actually getting to the point that I don't know if Alan Turing might have foresaw this, but we're getting to the point where computers might have too much mentality in order to pass the Turing test. So instead of saying, well, I've had conversations with these 2 rooms, and this conversation over here was worse than this conversation over here. So the room with the worst conversation, I'm going to say that's the computer, and the computer would fail the Turing test. You technically could fail the Turing test with the same sort of situation where you're like, this conversation was awesome, this conversation was average. So I'm going to say this awesome conversation is the computer, because no human could be that witty and that funny and that amazing. And if you guess more than 50% of the time, you would still fail the Turing test. So one of the best places to kind of see where we are going in terms of computing power is what happened on Jeopardy when they had a computer take on some of the best champs of all time.
In Jeopardy's 47-year history, there has never been a contestant like Watson. With 15 terabytes of random access memory, the IBM supercomputer has gobbled up encyclopedias, dictionaries, books, news, movie scripts, and more. Why? To beat these guys, for one. Ken Jennings won a record 74 consecutive Jeopardy games. Brad Rutger has earned more than $3 million in prize money. But Watson isn't in it necessarily for the prize money from the real matches planned for next month. IBM says the technology could help speed up medical diagnosis and other challenging computer tests. So how does it work?
It's a massively parallel, probabilistic evidence-based architecture. That's a mouthful. But the way to think about it is it's taking that clue, it's taking that category, it's taking the surrounding clues in that category, it's dissecting it and understanding it from many different dimensions.
Watson, Brother, and Jennings played demo round for the press, and Watson didn't hold back.
I've never said this on TV. Chicks dig me for 200. Kathleen Pena's excavation of this city mentioned in Joshua showed the walls had been repaired 17 times. Watson, what is Jericho? Correct. 400, same category. This mystery author and her archaeologist hubby dug in hopes of finding the lost Syrian city of Urkesh. Watson, who is Agatha Christie. Correct.
For Jennings, playing Jeopardy is old hat, but does playing against something that's the size of 10 refrigerators give him pause?
I did not play Watson until this morning. Until an hour ago, I had never picked up a buzzer against Watson. And it turns out to be like playing a very good human player. It knows its stuff. To get on the stage, you gotta know your stuff. But it can be beaten both on the buzzer and on the quiz, it turns out.
If you're a player, do you bet on yourself?
I don't know if this is Vegas line, but always bet on humanity.
Rucker didn't let on like he was the least bit intimidated.
I think there's a little bit of having to strike the blow for humanity against the machines going on here. But from the rehearsals we've done in the game playing, Watson is pretty much just a really good Jeopardy player. So it's kind of the same thing, but I guess there is a little extra pressure at having to represent the humans against the machines.
Host Alex Trebek isn't intimidated by the processing power either. He has seen all kinds of contestants take the stage.
I think the most intriguing thing about this challenge on Jeopardy featuring Watson and two of our best players ever is where do we go from here? How do we follow this? But I'm sure that within a couple of years or so, we'll figure something out.
Indeed they will, unless, of course, Watson figures it out first. Watson, the Associated Press.
All right, so you saw those two Jeopardy contestants. Those are literally the two best players of all time. I think not the most winningest players. I think that was a new guy that just came in last year. But I think Jennings still holds the record for most consecutive victories. So literally, two of the greatest Jeopardy players of all time. If you used Jeopardy as a Turing test, if you took a look at just their answers as your Turing test, Watson would fail the Turing test, absolutely. But not because he didn't do, or the computer didn't do well, but because it did too well. So they talk about how, he was just a very, Watson is just a very good player, just a very, a good Jeopardy player. Going up against the two best Jeopardy players of all time, this is what happened.
In the battle of man versus machine game show style, Machine is coming out ahead on the television show Jeopardy! Watson, a creation of IBM, has a commanding lead over humans Ken Jennings and Brad Reuter when it comes to bucks, some $35,000. But his database of trivia knowledge not perfect in a round of Final Jeopardy!
Its largest airport is named for a World War II hero. It's second largest for a World War II battle. And you have done what is...
All right, so look at these numbers here. Ken Jennings goes in with $2,400. All right, $2,400 going into Final Jeopardy.
Chicago, that is correct. I have to speak.
Brad Reuter, $5,400 going into Final Jeopardy.
He came up with the correct response, did he? Yes, and he responded.
All right, over 36,000. Right, so multiples of what these two champions got. So if I was told that there was this program that was made that could perform Jeopardy, and it was a computer program, and I was given those scores at the end of the contest, and they were asked, which one do you think is the computer program? I would say, yeah, I think it's this one right here. And it would fail the Turing test because I identified which one was the artificial intelligence. But notice that now it's failed not because it couldn't do Jeopardy, it's failed because it's done it too well. So is the Turing test necessary now for mentality? We might have gone past the point where it applies because some of our programs are just getting too good. I'll give you another example. Tesla, the automatic driving cars. If you take a look at collisions per mile, they're better than humans at driving. So they would fail the Turing test if it was driving, but not because they're not as good as humans.
What is Toronto?
All right, so last thing I want to point out about this. Number one, if you're interested in artificial intelligence and you're interested in psychology as well, there's an entire area of psychology that deals with interactions with computers, and the interactions with artificial intelligence, the prejudices and the sort of biases that come up with artificial intelligence are astounding, and they're like this new frontier in understanding human behavior. So there was, just to give you an example, there was a hitchhiking robot that hitchhiked in Canada, right? So literally a robot that would just kind of like stand there at the side of the road with the thumb out, and you would drive up and you would pick it up and you would go to wherever you were going, and then you would drop it out and it would pop its thumb out again, and another driver would pick it up. Traveled all the way across Canada, crossed into the United States. I think within a couple of 100 miles it was destroyed. It was straight up gone. So who would do that, right? Why? What's with this hate that some people have towards artificial intelligence? It's a really interesting psychological question. And you'll see in this report here, you'll see a taste of that. Because clearly, Watson decimated these other players. And they did not show one question that Watson got correct. What did they show? They showed the one he got wrong. They showed the one that was Chicago, but he thought it, Watson thought it was Toronto. And interestingly, though, as a psychologist and as somebody that would investigate artificial intelligence, notice that this is a plausible answer, right? Watson got it wrong, but he still mentioned a city. Watson got it wrong, but they still mentioned a city with airports in it, right? So this isn't what is Avengers Endgame, right? It didn't get it completely wrong. It got it wrong very much in a human way. So again, Watson might be doing cognition the same way that humans are doing it, just at a very, very much higher level. All right, so that is all that I want to cover for today. Any final questions or comments before we wrap it up? All right, so that is it for today.